Hey guys, how's it going? In today's video, we'll be talking about induction, a new concept in the topic of methods of proof. A lot of students, they get confused with the word multiple and divisible in different sort of questions in induction. And after watching today's video, I guarantee there's going to be no confusions. So we'll start with example 1. It says prove 3 to the power of n minus 2 to the power of n is divisible by 5 where n is a positive integer. Okay, so it says n is a positive integer. First thing I would do is I let n equal to 2x, in this case positive integer, so it's always, we multiply by 2, always becomes positive. Rewrite this as 3 to the 2x minus 2 to the 2x is divisible by 5 for all positive integers in this case. So n is greater than or equal to 1. Now what I'll do is let n equal to 1. 3 steps in induction. We know that step 1, we do the initial value. Step 2 is assumed for k and proof for k plus 1, and 3 is the final statement. So we'll start with step 1 over here. N equals to, so sub 1 into this. So we have 3 brackets, oh sorry, not brackets, 3 to the power of 2, or 3 squared minus 2 squared, which in this case is 9 minus 4, which equals to 5, which is divisible by 5. So therefore, true for n equals to 1. Step 2, we assume n equals to k. That's always the thing in induction. You always step 2 is always assumed for n equals to k. Rewrite this over here. So we have 3 to the 2k minus 2 to the 2k equals to some constant 5p. It's divisible by 5. So 5p, and we'll take p as a some constant. Now that we've done that, now we need to prove for n equals to k plus 1. Proof for n equals to k plus 1, we'll write this down as 2 to the k plus 1 minus 2 to the k plus 1. Further simplify this, we get 3 to the 2k multiplied by 3 squared, which is 9, minus 2 to the 2k, 2 to the 2k right here, multiplied by 2 to the 2 squared, in this case, which is 4. So this is what we get for that. Rewrite this over here. 3 to the 2k minus, we have over here, my bad. Sorry, we'll jump a step, get straight into it. So we know that 3 to the 2k minus 2 to the 2k equals to 5p in this case. So we can rewrite this as 5p brackets plus 2 to the 2 to the power of 2k minus, we can go 2 to the 2k multiplied by 36 in this case. We'll go to the next step over here. We can come back, we have this then equals to 45p plus 2 to the k multiplied by 5, which then equals to 5 brackets 9p plus 2 to the 2k. We've got to 5 are out here, multiply. So therefore, step 3, we write like a little paragraph just to explain what we've done, step 1 and step 2. So true for both S1 and S2, hence by mathematical induction, induction, true for all positive integers. So that is how you do example 1, which is about divisible. Now we'll go on to example number 2. So looking at this next example, it says prove n cubed minus n is a multiple of 6 where n is greater than or equal to 2. A little different, it's got a little multiple. Start with, again, step 1. Relatively straightforward. Let n equal to 2, sub that in to this over here. 2 cubed minus 2 equals to 2 times 2 is 4 times 2 is 8 minus 2 is 6, which is a multiple of 6. Therefore, true for n equals to 2 in this case. Step 2. Assume n equals to k. Come back over here. We have k cubed minus k equals to 6m. Again, we need to sub in some integer multiplied by 6, multiplied by 6, where m is always going to be a positive integer. Got that down. Now we've got prove for n equals to k plus 1. N equals to k plus 1, this then becomes k plus 1, all cubed minus k plus 1, which is a multiple of 6. So that's what we're trying to prove, sorry, multiple of 6. Come back over here, let's just expand the left-hand side. K plus 1, k squared plus 2k plus 1, correct? When you expand k plus 1 all squared minus k plus 1, correct? Next step, k cubed plus 2k squared plus k squared plus 2k plus 1, in this case, minus k minus 1. Then I have k squared minus k plus 3k squared plus 3k. 1 and 1 chop off. We know k, sorry, this is going to be k cubed, my bad. K cubed minus k, as we developed over here, is equals to 6m. So this then becomes 6m plus 3k squared plus 3k. In this case, factor out the 3k, 6m plus 3k brackets k plus 1. Now that we know, since k is a positive integer, sorry, k plus 1 is a positive integer, we then know that, I'll come over here, we then know that k brackets k plus 1 is going to equal to 2n, where again n is some positive integer. Now that we know that, let's come back to this value over here. So we then have 6m plus 3 brackets 2n in this case. 6m plus 6n divided by both sides by 6m plus n. Again, 6 is a multiple of this over here. Therefore, multiple of 6. Step 3, final statement, we go if, by mathematical induction, is true for n equal to 1, true for n equals to 1, and step 2 was true for n equals to k plus 1. Therefore, it's going to be true for n greater than or equal to 2. Coming back to multiple and divisible, we've seen that in both cases, example 1 and example 2, we had 6 or some constant multiplied by another variable inside, which then means that if a number, so let's just say if x is divisible by y and has no remainders, then we know that x is going to be a multiple of y. So basically, multiple and divisibles are basically the same thing. So there should be no, if any students that get questions that say multiple or divisible, just treat it as a multiple question. If you're comfortable with being familiar with divisible, just use the same process and you get the same answer. So that is how you do these two examples over here.